All right, hi everyone, welcome to lecture 17. So in this lecture, we're going to define the concept of uniform convergence of a sequence of functions, and we'll sort of contrast it with pointwise convergence, and we'll prove the main theorem about uniform convergence, which is that uniformly convergent sequences of continuous functions have a continuous limit. So uniform convergence ends up being a very desirable property for sequences of functions that lets us actually say sensible things about the limit. Uniform convergence is also the condition that guarantees that, for example, the limit of the integrals of the functions in a sequence will approach the integral of the limiting function. So there's a lot of good stuff that you get from uniform convergence, which does not happen for pointwise convergence. But before we get there, I want to actually just once and for all kind of set down the definition of pointwise convergence, and especially so that we can kind of we can really look closely at it in detail and see exactly how it contrasts with the definition of uniform convergence. So if you remember from the previous lecture, we actually kind of looked at an example of a sequence of functions that converged pointwise to some function. And that example was designed to be a counterexample to the idea that pointwise convergence could possibly guarantee continuity of the limit, because what we had in that example was something like, Fn. So in the example from before, we had Fn of x was 1 minus x, absolute value of x to the n. And then f of x was like 0 for x in -1, 1. And 1 for x equals 0, right? So clearly f was not continuous, even though each fn actually was continuous. So, so I kind of alluded to the idea of pointwise continuity there before, right? What I said was for each x, a fixed x, right? If you fix a value of x, then the sequence of numbers fn of x approaches the number f of x. This is essentially the idea of pointwise convergence. So to state it formally, we would say, let's see, 24.1 sequence of real valued functions on S converges pointwise to F, which is, of course, also defined on S, if for each x in S, the limit of Fn of x as n approaches infinity. And remember, these limits are as n approaches infinity, right? This limit is f of x. Okay, so you basically treat each value of x completely separately, right? So for each value of x, you just get a sequence of the values of each of the fn's, and you don't care about what any of the fn's are doing or whatever f is doing at any other values of x. You only care about x itself, what's happening at the value x itself, right? So that's pointwise convergence. And of course, you can kind of see, I mean, it's not that much different. It just, it's a little bit more prim and proper, I guess, when stated this way. So as we saw before, this example shows us that pointwise convergence already fails to have some of the properties that we would like for convergence of a sequence of functions. In Tuesday's discussion, we also saw that the sequence fn of x is nx to the n on 0, 1 converges pointwise to f of x equals 0 on 0, 1. But the limit of the integrals, right? If you take the integral of each fn, so the integral from a to b, or not from a to b, sorry, from 0 to 1 of fn of x dx approaches 1, which is not equal to the integral from 0 to 1 of f of x. So you cannot, for pointwise convergent sequences, you can't necessarily pass the limit into the integral, right? Which is unfortunate. And it turns out that for uniformly convergent sequences, you actually can. Although we'll get to that much later once we actually define the integral, right? But so you can already see why pointwise convergence is just way too weak to really be useful for almost anything. I think it's honestly, in my experience, it's very rare that pointwise convergence, like the main situations in which pointwise, you want to even refer to pointwise convergence are just like, if you take a sequence of functions and you want to first prove that it actually has a limit, then you can show that it converges pointwise to something. But then after that, what you might want to do, once you sort of like show that the pointwise limit exists, is actually show that the sequence converges uniformly to that pointwise limit. That's like the main situation where I normally see pointwise convergence even invoked. Yeah, as you can see, it has a lot of issues. So let me just, as the last thing in this video, let's unpack the definition of pointwise convergence a little bit, okay? Because it'll help us kind of really compare it to the definition of uniform convergence. So let's specifically, let's sort of unravel what it means for this convergence to happen, right? So let's just sort of copy paste in the definition of convergence for sequences of numbers, right? So so in other words, fn converges to f pointwise on S if for every x in S, for every epsilon greater than 0, right? We want to say for every x in S, fn of x converges to f of x. So now I'm just like unraveling what that means by definition. What does it mean for fn of x to converge to f of x, right? Well, by definition, that means that for every epsilon greater than 0, there exists capital N, such that for every n greater than capital N, we have fn of x minus f of x is less than epsilon, right? So that's, you know, you can see that's what the definition becomes if you kind of like unravel it completely. So I'll just tell you as a sort of a preview for uniform convergence, we require that for every epsilon greater than 0, there exists an n such that for every n greater than capital N and for every x in S, absolute value of fn of x minus f of x is less than epsilon. So look how similar they are. Really, it's just this for all x and S that's moved, right, from at the beginning to towards the end, right? And this is just another example of why the order of quantifiers is important. Cannot emphasize this enough, right? So the gist of the idea is that basically now we have to be able to pick epsilon. Here it's like, since we let x be an s first, not pick epsilon, sorry, pick n, capital N, right? Since we let x be an s first, then we were allowed to pick our capital N like based on whatever value of x we happen to be given, right? But in this situation, we're only given epsilon, and we have to pick capital N before we know anything about what x can be, right? So that capital N better work for like every value of x that could possibly be chosen from S, right? So that's what it means for uniform convergence. The last thing I want to say is please do not mix up uniform continuity and uniform convergence. It's easy to do. In fact, this might seem a little bit rich coming from me because I myself committed this cardinal sin early on in the when we were first talking about uniform continuity. So please ignore my own errors. Okay, obviously I'll try my best not to mix them up whenever possible. For me, the issue is that like I'm very used to these ideas. So in my head, I absolutely know which of the two properties I'm talking about. I have the right picture in my head because I'm very fluent in the concepts. But for you guys, it's like even more important that you don't mix up the terms because you're still new with the concepts themselves. So I think there's a weird amount of like mental dissonance or like sort of psychological dissonance that can happen if, because the terms are so similar to each other. I mean, they even start with like CON at the beginning, right? It's like uniform con something. So, and there are some similarities in like why they're both considered uniform, right? It's something to do with like, for all x in S, or like for all x and y in S, etc. Right? So something, this uniform thing has something to do with like making a property, make it so that you can like choose a certain variable uniformly for all values of x in like a set or something like that, right? There's some kind of similarity there. It's sort of a kinship, but really they're very different concepts in the end, because in uniform continuity, you're sort of like choosing a pair of input values for a single function anywhere from the set S as long as they're close to each other. Whereas for uniform convergence, you're still only ever choosing a single input value, and then you're comparing the values of different functions in the sequence, right? So there's sort of like orthogonal to each other in that way. But yeah, anyway, so please try to ignore my mistakes. As they say, do as I say, not as I do, right? So anyway, so that's all for this video. In the next one, I'll actually define uniform convergence, in a bit of a nicer way than just this, I guess. And then we'll sort of look at an example of a uniformly convergent sequence and a non-uniformly convergent sequence according to the definition.